In this video, we're going to discuss Farkas lemma. Farkas lemma is one of the most important results in duality theory, and it is essentially equivalent to strong duality. Think about the situation where your boss asks you if a system of linear inequalities is feasible or infeasible. Now, let's say that you're smart and that in some way you're able to understand if such a system is feasible or infeasible. Now, everything you have to do is report to your boss. Let's consider separately the two scenarios. First, assume that the system is feasible. Now you can easily convince your boss that the system is indeed feasible by showing to your boss a feasible solution. Then your boss can easily check that you actually did your job and you're not just lying. In fact, your boss can just plug in the vector that you give in the system and check if the system is actually satisfied by such a point. Now consider the second scenario where the system given to you is infeasible. Of course, you can tell your boss that the system is infeasible. However, it's not obvious to find a simple way to actually convince your boss that you did your job and you're not just lying. And this is where Farkas lemma comes into play. Essentially, Farkas lemma will provide a certificate of infeasibility. This is done by showing that the infeasibility of a given system of linear constraints is equivalent to the feasibility of another. So to convince your boss that the system is infeasible, you can instead show that this other system is feasible. And we just discussed that it's easy to convince your boss that the system is feasible. Consider now a set of standard form constraints ax equal to b, x greater than or equal to 0. What I want to do in this slide is to show you a possible way of convincing your boss that this system is infeasible. Suppose that there exists a vector p that satisfies p transpose A greater than or equal to 0 transposed and p transpose B strictly negative. We will see that this vector p is the certificate that we're searching for. How can we show that? Consider the quantity p transposed AX. We know that p transpose A is greater than or equal to 0, and so if we assume that x is greater than or equal to 0, this product is greater than or equal to 0. On the other hand, we're assuming that p transpose B is strictly negative. So we can conclude that p transpose AX for any x greater than or equal to 0 is different than p transpose B. This directly implies that AX is different from B for all x greater than or equal to 0. In fact, if we multiply the left hand and the right hand of AX equal to B by P transposed, we obtain on the left hand P transposed AX and on the right hand P transposed B. So this argument shows that if we can find a vector P that satisfies at the same time P transposed A greater than or equal to 0 transposed and P transposed B strictly negative, then the standard form constraints have no feasible solution. So this vector P is a certificate of infeasibility. So this is great. If we can find such a vector P that satisfies these conditions, then we do have a certificate of infeasibility. However, it's unclear at this point if such a certificate always exists for any system AX equal to B, x greater than or equal to 0 that is infeasible. Farkas lemma then says that such a certificate of infeasibility P is always guaranteed to exist whenever the standard form problem is infeasible. So essentially there always exists such a certificate of infeasibility P no matter what system you start from. Of course, the difficulty then will be to find this vector. So now let's read the statement of Farkas lemma. Let A be a matrix of dimensions m times n and let B be a vector in Rm. Then exactly one of the following two alternatives holds. A. There exists some x greater than or equal to 0 such that Ax equal to B. And B. There exists some vector P such that P transpose A greater than or equal to 0 transposed and P transpose B strictly negative. In particular, in case A, our system is feasible, while in case B, our system is infeasible. Let's now prove Farkas lemma. In Farkas lemma, we need to show that exactly one among A and B holds. So the first thing we're going to show is that A implies that B doesn't hold. Once we're done with this implication, we're going to show that if A doesn't hold, then B holds. So in our first implication, we are assuming A. To show that B doesn't hold, we're going to take a vector P with P transpose A greater than or equal to 0, and we're going to show that P transpose B is greater than or equal to 0, which then implies that P transpose B cannot be negative. So if there exists a P such that P transpose A is greater than or equal to 0, then P transpose B can be written as P transpose the AX, where X is the vector greater than or equal to 0 such that AX equal to B from point A. Now P transpose A is greater than or equal to 0 and X is greater than or equal to 0. Therefore, this product is greater than or equal to 0. Therefore, we have shown that P transpose B is greater than or equal to 0. Therefore, B cannot hold. Next, we show the next implication. So we assume that A doesn't hold, and we show that B holds. So we're assuming that A does not hold. So there is no x greater than or equal to 0 such that AX is equal to B. Now we consider the pair of problems where the primal is min P transpose B subject to P transpose A greater than or equal to 0, and the dual is max 0 transpose x, which is just 0, subject to AX equal to B and x greater than or equal to 0. We have just seen that there is no x greater than or equal to 0 such that AX equal to B. Therefore, the dual is infeasible. So we know that the primal must be either unbounded or infeasible. But clearly the primal is feasible, because the vector p equal to 0 satisfies the constraints. P equal to 0 is a feasible solution to the primal. Therefore, the primal is unbounded. Since the primal is unbounded, we have feasible solutions with arbitrarily low cost. Therefore, there exists a vector p feasible for the dual whose cost is negative. Therefore, this vector p satisfies p transpose A greater than or equal to 0, since it's feasible, and p transpose B negative, because it has negative cost. And this is exactly what B says, so B holds. And this concludes our proof of Farkas lemma. Let's get back to the slides. Next, I want to discuss the geometric intuition behind Farkas lemma. Let's write down AX as the sum of the AI xi for I that goes from 1 to n. As always, here AI denote the columns of A. Now the existence of a vector x greater than or equal to 0 that satisfies AX equal to B means that the vector B lies in the set of all the non-negative linear combinations of the vectors A1 until AN. For example, let's look at this picture. We have A1, A2, and A3. Now the set of all the non-negative linear combinations of these three vectors is the set of points that lie in this region over here. So then, case A of Farkas lemma is the case when the vector b lies in this region. So now consider the case where the vector b cannot be written as a non-negative combination of the vectors ai. Then it looks obvious from the picture that we can find a hyperplane that separates our vector b from the cone of the non-negative combinations of the ai's. In this picture, for example, we can take this hyperplane over here, which is defined by p transpose z equal to 0. Then we have that the scalar product of p with b is strictly negative. On the other hand, the scalar product of p with any vector ai is greater than or equal to 0. In matrix form, p transpose A greater than or equal to 0. And so this second case is exactly case B of Farkas lemma. The structure of Farkas lemma is of the type exactly one of these two alternatives hold. And this is why results of this type are also called theorems of the alternative. There are several interesting results of this type, and you can also find some in your exercises, especially exercise 4.26, 4.27, and 4.28. Note that any theorem of the alternative that says exactly one among the two alternatives A and B holds can be restated with an if and only if. In fact, equivalently, you could say that A holds if and only if B doesn't hold. And with this, we conclude our video on Farkas lemma.